Yeah,
Yeah, it has been
it
done.
says here, yeah.
Yeah.
YouTube live. Okay.
YouTube, yeah.
Should we start, sir?
Yes, please.
Yeah. So good afternoon, everyone, to the lecture series on atmospheric dynamics and its applications to climate sciences. This is the fourth lecture in the lecture series. This lecture will be delivered by Professor Dr. D.V. Bhaskar Rao, sir. And before we proceed for the lecture, I would request Dr. Samrendra Karmakar, sir, from Bangladesh, to please deliver his welcome address.
Thank you, Rohini. I think honorable members of the SAMA, President of SAMA and also GS General Secretary, Dr. Das, and our distinguished speakers and audiences, good afternoon and namaskar. Actually, it is my pleasure to welcome all of you to today's lecture on the dynamic meteorology and its application to climate sciences. We are truly excited to have such a distinguished audience here today to delve into one of the most fascinating and complex fields of atmospheric science. Practically, dynamic meteorology is the study of the motion. We know of the atmosphere and its relationship with the physical and thermodynamical processes that shape weather patterns. As we are all aware, the understanding of atmospheric dynamics is essential for predicting weather and studying climate change, which has become increasingly important in today's world. And today's lecture, that is the component equations of the equation of motion, is very important, especially for the beginners. And it is really interesting, and I used to enjoy while I was a student in this subject. And today actually we are fortunate to have the distinguished speaker, Professor Dr. Bhaskar Rao, an expert in this field, with us today. Professor Bhaskar Rao brings invaluable experience and knowledge, and we are eager to hear insights on the key principles that govern the atmospheric motion, from the equations of motion to large-scale circulation patterns. Today's lecture will be an opportunity for us to explore complex ideas in a way that sparks curiosity and deeper understanding, bridging theory and practical applications in meteorology. It is a great chance for the meteorologists, students, professionals, and anyone with an interest in weather systems to gain a clear understanding of the dynamics of the atmosphere. And these components of the equations are very important, especially for the dynamic model that is being used nowadays for forecasting of tropical cyclones and other weather phenomena. This is really interesting, very interesting, and the what we call non-linear differential equations that can be obtained from these equations of motion, which are very much useful for the model to run. Okay, so I encourage all of you to engage with the speaker, ask questions, and think critically about how the concepts presented today apply to both current weather patterns and long-term climate phenomena. Without further ado, I would like to once again extend my warm welcome and invite Professor Dr. D.V. Bhaskar Rao to begin today's lecture. I hope all of us will find this session both enlightening and inspiring. Thank you very much. Sama, long live Sama. Thank you very much.
Thank you, sir, for such an inspiring welcome address. We all know Professor Bhaskar Rao, sir, but yes, I would request Dr. T.V. Lakshmi Kumar to please introduce our speaker.
Thank you, Dr. Rohini. So I'm very happy. I'm very happy to introduce today's speaker, Professor D.V. Bhaskar Rao, who is one of my teachers in Department of Meteorology and Oceanography. So, sir, Dr. Bhaskar Rao, sir, currently working as Honorary Professor in Department of Meteorology and Oceanography, Andhra University. So Professor Bhaskar Rao served Andhra University in several capacities as Professor, Chairman, and Head of the Department during 1976 to 2008. He initiated teaching and research programs in atmospheric modeling and numerical weather prediction and mentored 18 doctoral students and several MTech and MSc students at Andhra University. He is known for his contributions to atmospheric modeling, tropical cyclone prediction, and numerical weather prediction. Professor Bhaskar Rao worked as visiting professor at Jackson State University, USA during 2009 to 2013. Dr. Bhaskar Rao published 2 books. One is Numerical Weather Prediction, published by the Indian Meteorological Society, and the other is Mesoscale Modeling of Atmospheric Process in India, published by the Department of Science and Technology, Government of India. And Professor Bhaskar Rao made different chapter contributions in 5 books and published more than 100 research papers in very, very highly reputed journals. He had been recipient of many research recognitions. To name a few, Dr. B.N. Desai Award by Indian Meteorological Society, Fellow of Andhra Pradesh Academy of Sciences, Fellow of Indian Geophysical Union, Best Academician and Best Researcher Awards by Andhra University. Professor Bhaskar Rao served as Distinguished Visiting Professor in the Indian Institute of Tropical Meteorology, Pune during 2014 to 2016 and guest faculty at University of Hyderabad during 2013 to 2023. Sir has served on many scientific and selection committees of the DST, SERB, IMD, IITM, and several universities in India. He is currently serving as the chief editor of the Journal of Indian Meteorological Society, Vayumandal, basically originated from within India. So with this, I invite Professor D.V. Bhaskar Rao to proceed for his talk. Thank you.
Thank you, Dr. Lakshmi Kumar. Okay, just Zoom, share. Share. I hope my people
Yes, sir.
visible and
Yes.
also that I am audible.
Yes.
First, thanks for facilitating my lecture today. Actually, it was scheduled for tomorrow. For some personal reasons, I have requested and it has been kindly accepted. Today, anyway, I'm very, very happy to be a part of this lecture series on atmospheric dynamics and its applications to climate science. I have been asked, actually, the topic has been given to me. It is the component-wise equation of motion and a rectangular Cartesian coordinates, especially Eulerian and Lagrangian derivatives. Okay, this is a very, as Dr. Karmakar has said, it's very important as well as of interest because equations of motion are the basic equations which we time and again use in various kinds of dynamical analysis, more so in weather prediction or any kind of modeling. So I will try to make my talk as simple as possible because Dr. Karmakar has said there are going to be many students who are going to be a part of the learning process of the dynamic meteorology. So if they do not understand, maybe they can raise the questions at the end. I will try to make my lecture as simple as possible. So first I will start with making some statements, fundamental statements, which all of you would agree. And if you don't, definitely I would be very happy to clarify. We are going to deal with atmosphere, which is a continuum of air. The air that we are talking about is a mixture of gases and which is held It's coming in. What is saying? This atmosphere, the air that is what we are calling as a mixture of gases is held close to the surface of the earth. Otherwise, it would have gone into the space. But due to gravitational attraction of the earth, the atmosphere is clung to the earth. That's we know. And we are talking about whether actually denotes the in situ state, the current state of the atmosphere, mostly expressed in terms of elements such as temperature, wind, rainfall at a particular place. Climate, though we use many times weather and climate synonymously, but climate is different because it signifies the average of the weather, which we say a current state, but climate belongs to a long period average state. And we know what we call weather. I have just stated. The properties of the atmosphere change continuously in space and time. And that means whatever that is there, the air we are calling what is the content of the atmosphere, it would be changing. The properties of the atmosphere like temperature, wind, humidity, etc., would be changing continuously in space and time. And the atmosphere, we know that it is not static, but it is in constant motion. And the motion of the atmosphere is mainly driven by solar energy, or the energy coming from the planet Sun, and which actually there is a lot of radiative process that go on, and which has been dealt with atmospheric physics. Under atmospheric physics, radiation has been dealt elaborately. And because of the sun's energy, it causes, because of the differential heating at the Earth's surface and the atmosphere, it causes density differences. And the density differences lead to the air to be in motion. And this atmosphere, what we observe, is in constant motion. It is not static. So if something is in motion, the atmospheric dynamics, that means the dynamics part comes into picture. So we are going to concern ourselves with the study of the atmospheric motions and the relationship between two heating and forces. So there is two parts. One is heating and forces. All this a little later we will realize why I'm making these two words separately. So we know that atmospheric dynamics are the dynamics of the atmosphere, which concerns the study of the atmospheric motions. Mostly relates or is connected to the heating and the forces that make it move. And some more concept here I want to introduce. Many times we use this, a parcel of air. In meteorology, the usage of a parcel of air is very, very common and is very useful to analyze and understand the atmospheric process. What is this parcel? The parcel is supposed to be large enough to contain large number of molecules, but also it is small enough so that the properties inside it are homogeneous. That means whatever the properties of the air parcel, they are going to be the same all through the volume of the parcel. But it's not a very small, but it is large enough. It contains large number of molecules. So it is very difficult to say how much size it should be, but somebody said 1 cubic foot or something should be reasonably good, but that need not be taken very seriously. And the air parcel is assumed to have properties such as temperature, humidity, and pressure, but they are supposed to change as the parcel moves along with the atmospheric motion. So the properties inside, though are homogeneous, but the total properties of the air parcel, such as the temperature of the parcel, humidity of the parcel, and pressure of the parcel, would change as the parcel moves through the atmosphere. And following this, we can say that the atmospheric can be considered as a bunch of air parcels, as a bundle of air parcels. So the atmosphere can be considered a content of many number of air parcels. And the characteristics of the atmospheric flow, that means the combined properties of all these parcels as the atmospheric moves along, the characteristics would be determined by the characteristics of these parcels. So the concept of an air parcel is very important. We are going to use it here. And a parcel of air, it is supposed to be that it is insulated from the environment. That means the volume of the air parcel which we are considering, it is actually having some, there is no boundary, but it is, we suppose that it has an invisible boundary with the surrounding environment, and that the parcel boundary is flexible, permitting the air inside to expand or contract. That means the volume could change, it could increase or could decrease as its relation with the surrounding environment. So the parcel is, although it is supposed to be insulated from this, it is insulated, but it has the flexibility in terms of its contraction or expansion. And at any particular place, the parcel and the surrounding environment should have the same pressures, because at any particular place, if something has to be in some particular kind of a stable state, the parcel inside, the pressure inside the parcel and the environment, surrounding environmental pressure should be same. If not, if the parcel temperature is more than the environment, so the parcel inside, it is lighter than the environment, and it would rise. Similarly, if the parcel is cooler than the environment, it would be denser, and so it would sink. So these are the basic things, how the parcel would move in relation to the surrounding environment. These are some fundamentals which most of you are aware, but should be known before we go forward. Now, with these concepts we have seen, I go to our lecture today. I have been asked to talk about the Lagrangian and Eulerian forms or descriptions of the atmosphere. So we have been talking about the atmospheric flow, and now I say that it can be observed in two ways. One way is to focus on one specific fluid parcel, follow it as it moves in the atmosphere. So we make some statement, atmospheric flow can be observed in two ways. One way, that the Lagrangian form, is to pick up a parcel and follow it as it moves through the atmosphere. So you are fixing yourself to a particular fluid parcel and following its properties as it moves through the atmosphere. So this is called a Lagrangian description. And any Lagrangian information concerns the nature and behavior of the fluid parcels, because as the fluid parcel is passing through the atmosphere, it is moving through the surrounding environment, it changes its characteristics. So we would be observing, or we would be taking the information of the air parcel as it passes through a fluid environment or atmosphere, whatever it is. For example, if we say that, we can say a cold air mass is coming from the north. So here we are saying an air mass. So air mass is a cluster of air parcels which is cooler and it is coming from the north. That means it's some kind of air mass. It is very common for us to say, so air mass is moving from into our place, so it will be colder tomorrow. We are talking about a bunch of air parcels that are moving and they are coming, which are colder than what we have at this particular time. So if a colder air mass is coming from some other direction into the place where we are, and we can say that the cold air mass is moving. See, this is only an example how we talk about the Lagrangian way of talking about the atmospheric flow. Actually, this particular Lagrangian description in the fluid dynamics came from a famous scientist. He's an Italian-French mathematician, physicist, Joseph Louis Lagrange, in the 18th century. So he actually conceptualized this and gave us. In contrast, what is the Eulerian form? It is the observation of the atmospheric flow by seeing the pattern as a whole. If you have an area of the atmosphere or the volume of the atmospheric flow, you are going to look at the pattern as a whole. That means throughout the entire volume of the atmosphere which we are considering, and we are going to talk and say something about the characteristics of the volume of the air which is under consideration. So previously, Lagrangian means we are talking about one specific a fixed air parcel and how it changes its characteristics as it passes through the fluid or the atmosphere. But in contrast, we are not talking about parcels, but all the parcels put together in a volume of the atmosphere, and how the characteristics we can observe, how we understand, how we describe that is the Eulerian form. So Eulerian form generally concerns like the properties of the velocity, how the wind direction and speed are there, how the pressure distribution is there in the horizontal plane or the vertical, temperature, how it is varying with time and space. So we are going to say something about the characteristics of the fluid in a volume element, and how the pattern is going to look like, and how the properties vary in time and space in that particular volume. So we are going to, these two are contrastingly different concepts. And a good example for the Eulerian is, for example, our location, the temperature will decrease. So in the next few hours, the temperature may fall, the temperature may increase at a particular location. So that's the Eulerian way. So we are not talking about the air parcel individually, but we are going to talk about the a volume element of the atmosphere, and inside that you can talk about the weather or the characteristics of the atmosphere at a particular location inside the volume element. So this is the Eulerian form. Contrastingly, these two are very, very different. The Eulerian description is actually was given by a Swiss mathematician, Leonard Euler. He's a famous fluid dynamics scientist. So these two, Eulerian and Lagrangian, came from two different fluid dynamics scientists. So now we can say the Lagrangian perspective, generally, because I said it is a specific parcel of air. For example, a good example they gave is, suppose an apple is falling from a tree. We will describe how the apple is falling from the tree, from its place to the ground. We say that what is the height of the apple as a function of time, how with what speed it is coming down to the ground from the tree. We talk about that. So we are talking in that particular context. We are talking about a solid object that is passing through the atmosphere we are considering, and that particular description is a Lagrangian description. So it is something like what is going to do with an apple coming from a tree. In contrast, the Eulerian description is more natural to the fluids than the solid objects. A solid object is more well described by the Lagrangian form, but both are useful for us. So we are going to talk about both of these things. So the Eulerian is, though it's more natural fluids or the atmosphere, it actually makes the analysis easier. That means if we have a bunch of data in a volume of the atmosphere, it makes the analysis easier to understand how the properties of the atmosphere exist inside that volume, inside that, how the flow pattern is, with what velocity, with what direction, how the temperature is changing, etc. We would be able to do this from, if you use a Eulerian perspective. Actually, this particular way is useful to describe the atmospheric flow using some mathematical equations, what we call partial differential equations. I know that in the last 2-3 lectures, something, at least last class, Akhilesh could have given something about the vector form. So it is actually all are interconnected. So I think I presume that all of you know what are the differential equations, what are the partial differential equations. And so the Eulerian perspective actually is very much useful to describe the atmosphere in the way that it actually allows us to use some mathematical equations to describe or understand the behavior of the atmosphere. Well, the Lagrangian and Eulerian are entirely different. One follows the single parcel, so there could be many parcels. We follow the different parcels at the same time. But why do we need two approaches, at least in the meteorology? Why do we need both the Lagrangian or the Eulerian, or can we do with one? Here, there is a way. One is we apply laws of physics to a fluid parcel. Normally, the fluid parcel is going to become warmer or lighter. It is going to be denser. It rises down. It is concerns of a fluid parcel. And so the laws of physics, we are going to here, you have to be very, very careful. I am talking about the laws of physics here. So the laws of physics, when we want to apply to the atmosphere, it is more important for us to use the concept of the Lagrangian, because it concerns with the individual parcels, and the laws of physics like heating, etc., would be more applicable to the individual parcels. So here they gave an example. If you apply heat to a fluid parcel, the temperature will increase. So here we are calling about a single individual air parcel, and its temperature is increasing because you are giving heat to it. That is the Lagrangian way of describing. And in meteorology, in understanding the weather, we need this particular way of representation. So the laws of physics, their applicability is very, very important for us. And apart, then why do bother about Eulerian? But we also have, this is individual parcel. It is going to change its characteristics. The temperature will increase, density will increase, humidity will increase, whatever these things are changing. That is a Lagrangian, we all agree now. But these fluid or air parcels are changing, or they are moving. When they are moving, why they are moving? They are subject to some kind of a force. So when anything comes into a form of movement, motion, the laws of dynamics come in. So the laws of dynamics, which actually we know the Newton's laws of motion, how the acceleration would take place, first law, second law, third law, etc. And in meteorology, we mostly use the Newton's second law of motion, as you all know. So when it comes to the atmospheric motion and understanding how the atmospheric motion takes place, what kind of forces play in order for the air parcel to move, then comes the Eulerian form. So when the dynamics come in, we need the Eulerian approach. When it comes to the physics, then we need the Lagrangian. So we need both of these approaches to be applied so that our understanding would be much better than of the individuals. So what we do is, when we develop the equations of motion, we will do it in 2 steps. That is, apply the known laws of physics to the fluid parcels and translate the results into Eulerian form for mathematical analysis. So while doing this, we are combining both of them. We apply the laws of physics to individual parcels, and then we treat all these bunch of particles and then use them into a mathematical analysis. So that is the Eulerian form. So we are going to use both these together. So with this background, now I say that how these two Lagrangian and Eulerian perspectives, how these are related to each other. Are they completely different? Can we make a mathematical operation involving both of them? Then it is possible. I'm going to talk about it. That's going to be using a mathematical operation called material derivative. So I presume that all of you are aware or have considerable good knowledge of the differential equations, derivatives, etc. So if we see the Lagrangian frame, the blue dots are the positions of an individual parcel as it moves in the atmosphere. So here it starts and it goes through different points to reach at some place in a given time. So we are following in the Lagrangian form the parcel and its path in the atmosphere. So you know the properties of the parcel at various points as it passes through. So how to quantify the properties? Then using these properties of the parcel, how to quantify the atmosphere around? These are the two questions we have. So in the Lagrangian frame, what we see here is, so here is the starting point at various points. This is the one. We can just describe each individual parcel through some position vectors. That means from the starting origin point, we can see where the parcels are placed. So from the starting point, how this parcel is moving, you can have what is the distance between and in what direction he is moved with respect to a starting point. So the properties of the atmosphere at different points through position vectors with reference to the origin now are known to us. And at any particular point, if you have a parcel, you can take it to the origin and then some particular properties like mass are invariant as the parcel moves through. So you can see what is the invariant property and then how the parcel is changing through. For example, this shows parcels from different locations. Each color, for example, indicates one parcel. All of them are starting somewhere here. So they have different paths. In course of time, they have different paths taken. And we have the information of the properties of the air parcels at various position vectors of each individual parcel. So at each individual, at different positions, as the parcel passes through, we can just have the information of its characteristics. But suppose you want to know what are the characteristics of the atmosphere in terms of temperature, pressure, wind, whatever it is, at least of the air parcel, not the wind, temperature, humidity, density, etc. at this particular point, how to get it? So we can use as I said, the starting point, you have the position vectors. So we know the characteristics of that. So is it possible for us? So this particular map shows how we can have the information of the parcels, individual parcels in a volume of the element of the atmosphere. And if you want somewhere at some particular point, you see, it depends on, you have to now again, you know it here, only using these two, you have to get the value at the position you want. This is good. This is good, but this is good for developing some particular kind of theories, how things would happen in the atmosphere. Is good for visualizing the fluid motion. That means how the fluid is moving in that particular volume, how the fluid is changing its course. That can be understood by visualizing the path of each air parcel. And we know the history of each fluid parcel. That means what are the characteristics, etc. But the problems are it is difficult to keep track of each individual parcel using a coordinate. That means for each of the particle, you have to have an origin and you have to have a position vector. That means how the parcel is changing in time. And so you have to have a coordinate system for each parcel. Then only you will be able to identify some of these things. It is very difficult for us to have so many coordinate systems to track of so many parcels. And this particular one will not be able to provide us if any of the two parcels are interacting with each other. That means if they happen to meet or pass through, come across one another, would they exchange the properties? Is it possible for account? So Lagrangian does not give us any information about any possible interactions between any of the parcels, any of the two parcels. So that's another problem. For example, if the parcels are too small in number, if you consider only two lesser number of parcels, then it would be difficult for us to analyze the fluid of the region and to understand the properties of the region as a whole. So that's one. And suppose if all the fluid, these air parcels bunch together, that means they come closer together and then they do not disperse, then how do you be able, you will not be able to get the information about the complete volume of the atmosphere, but you will be able to get more information from a few isolated areas where they bunch together. So these are some advantages and disadvantages. And a good example for the Lagrangian frame is weather balloons. Weather balloons, all of you know, they are being launched every day with some instruments right from the ground. They go up and provide us the data of the meteorology at different heights. So the balloons are supposed to passively transported. That means it has some lighter hydrogen-like gas inside. So it rises through. And so it could be considered as an isolated parcel. And so whatever the measurements that come from the balloon as it passes through the atmosphere, we can say it is a Lagrangian frame. Good example. In contrast, Eulerian frame, we come forward. So this is the parcel and this is the path of the air parcel 1. We have a coordinate system here. And now in the Eulerian, what we are going to do, we are going to blend all the information that is coming from all individual measurement. Though you have the air parcels, we have measurements at different particular locations, and we are going to blend all that information and then try to describe the properties of the atmosphere in the volume under consideration. So mostly this constitute a number of measurements that are being made some fixed locations. So locations are being fixed. You take measurements in time, and then so that means in space and time you have the observations at fixed locations. Then use all of them using a mathematical coordinate system like this. So in that particular case, you can have only one coordinate system that would help you to make an analysis of all the observations that you get, and so that facilitates a good analysis. So here the same picture as before, but you have only one coordinate. But with respect to this, you have the measurements at each of the point. At each of the point that the air parcels pass through, you have an observation, so you can blend all of them. And the Eulerian frame is also useful for developing some theories. And it has an advantage that it uses only one coordinate system, unlike the Lagrangian, which needs the number of coordinate systems as of the number of parcels. And here the interaction of the parcels through surface forces can also be represented. Now here in this, the entire fluid is seen as a single volume. And since you have the value at every point in the field, there are no gaps of information like what we have in the Lagrangian. If all the parcels bunch together, you will have the gaps of information. But the Eulerian frame also has some disadvantages. It is difficult to keep track of a parcel, each parcel history, it is very difficult for us. For example, when we talk about something like air pollutant dispersion of air pollutants in the atmosphere, then you have to have a concept of the parcel and how the parcels would pass through in the atmosphere. That is Lagrangian. That would be useful. Lagrangian wave would be useful to understand something like pollutant dispersion. So Eulerian frame, we have the weather stations located at different already fixed locations in space, and measurements are taken at different known times across all the observing locations, and all that would be used to blend it together and make an analysis and to get an idea of the state of the atmosphere. So the Eulerian frame is different. We know both of these things, how we use the parcels to measure the atmosphere. We also use the weather station. This is like a small weather observatory weather station, which takes observations like wind direction, wind speed, temperature, humidity, etc. For example, this shows you a map, a Eulerian map. That means a spatial distribution of the temperatures over India. So where the higher temperatures, where the colder temperature is the higher temperature, the colder temperature. So how the temperature distribution, if you have the observations over the entire Indian subcontinent, they can be used to analyze and have a map like this. So that will give you an idea how the temperature distribution is there over the Indian subcontinent. Now, again, come to the point. Why again, this is again a question, why two frames? Because we know that whatever the frames of reference, the physical principles hold good. So if you use multiple frames, it will be help only improve our understanding. But in the case of meteorology, as we know, certain particular physical processes are better represented using a Lagrangian frame, whereas the dynamical part is being done using a Eulerian frame. So we come here now to use some mathematics. Most of you may be knowing. So here we consider a parcel here at a time t0. And this parcel moves to this location in time. So this is a Lagrangian derivative. A parcel starting at this point moves to this particular point from t0 to t1. So x at t0, x at t1. For example, this is a small, the x by two-dimensional one we are talking about. Don't worry in this. So the temperature difference between these 2 points, that means how the parcel changes its temperature. So T at T0 x T0, T at T1 x T1. So delta T is equal to T at T1 x T1 minus T at T0 x T0. So this is a simple mathematical form, and which gives us a Lagrangian derivative. So mindful, we are considering a parcel at 2 time points, the same parcel, how it is moving in the atmosphere, and we are trying to make it a mathematical form. Not a very difficult one. Most of you should be able to do it very easily. And we do some mathematics. We can write this delta t, we can express this delta t in a Taylor series and neglect some higher order terms. So delta t can be written using a Taylor expansion, dou t by dou t. Dou by dou t is a partial derivative of the temperature multiplied by delta t at the point. Dou by dou x of t into delta x, dou by dou y of t into delta y, dou by dou z of t into delta z. So we have the change of the temperature in all the 3 directions, and at the place where you are talking about at the initial starting point, what the parcel has. So if we neglect higher order terms, and if we say that the delta t is very, very small in the differential, to make it the differential, the same equation is being written here. And now dividing by delta t, we write this same equation, just divide this with delta t. So we have delta x by delta t, delta y by delta t, delta z by delta t. This gets cancelled. So we have delta T by delta of capital T by delta of small t. Capital T is temperature here in this particular case. Small t is time. So this notation is good. Considering delta T to be very, very small, this limit of these things as delta T tends to 0, calculus, we can write this as capital D by capital DT of capital T means temperature. This is temperature. This capital D by capital DT, I'm sure that in the last lecture, lecture 3, Akhilesh could have given you what is the total derivative, what is the local derivative, etc. in the vector algebra. He should have dealt. Unfortunately, I could not attend the last lecture, but this is very easy for us to understand from the basic calculus we know. So this is this equation. This equation can be simplified, or in differential form, we write it like this. So this is not a very difficult one, but we know here dx by dt is u component of the wind, dy by dt, the change of the distance in the y direction in a small time interval, that is, we call it v component. In the vertical direction, we call it the w. So u, v, w, or we know these things. So u, v, and w are the 3 components of the vector wind. And u is equal to dx by dt, v is equal to dy by dt, w is equal to dz by dt. That's very well known to us. So the equation which we are talking, this equation now is the same we are writing. Capital D by capital dt is equal to dou by dou t of t, u dou t by dou x, v dou t by dou x, w dou t by. So here, whatever that is, the first one, capital D by capital dt of the temperature is the Lagrangian frame. So previously you have we have started with this. Here we have started with this delta t. So on the left-hand side, we have been doing this. And so the left-hand side, we have this particular one is the Lagrangian form, how the parcel changes its temperature. And the first term on the right-hand side is the Eulerian frame. That means at one particular point, how the temperature changes in time. So this is the Eulerian form or the Eulerian frame. This is the Lagrangian frame. This is something what is called advection. That means how the property of the atmosphere moves with the wind field. So this is also a concept of advection. Probably most of you know before. So here this dt by dt is equal to dou t by dou t plus this u is nothing but a vector wind, just to make it, not this u. This u is only the journal component of the wind, but this u is a vector of the wind. So I should have written capital V, it doesn't matter. So capital D by capital dt of the temperature is equal to dou by dou t of t plus u vector v u dot delta t. So this is a this particular equation is a coordinate independent form. It is not a Lagrangian, Eulerian, but we have mixed those of these things. So we are connecting the Lagrangian frame, which describes the properties of the fluid parcels, with the properties of the fluid at a particular location. So these two are now mathematically, we have shown how these two things are going to be related. So the Lagrangian form material derivative is equal to Eulerian form total derivative plus advection. I think that much is one. So dt by dt, this is the Lagrangian form of derivative of the temperature. The Eulerian form of the derivative, that is dou by dou t. Local derivative, that's called, plus v dot del t is the advection, So this v dot del t is the advection. So how the temperature of the fluid, that means the material derivative is the rate of the change of the fluid following the air parcel. The first, the dou t by dou t is the Eulerian derivative, that is the rate of change at a particular point, and the second part is advection. How the properties change as it is being advected. A parcel is being advected. So if you want the temperature at a particular frame, so at a particular point, that means in the Eulerian form, we write dou by dou t of capital T is equal to Lagrangian derivative minus advection. So this is at a particular point, you're writing the derivative like this. Dou by dou t of t at this particular point is equal to the Lagrangian derivative of the parcel minus the advection. So this is the material derivative. So the same thing, term by term, we are explaining, showing a picture. So this Lagrangian frame, Lagrangian derivative. So what is the temperature this parcel would attain as it moves from this particular point to this particular point? So this particular, the temperature that is attained by the parcel as it moves from this particular point to here is called the material derivative. And the advection, we know the parcel is moving, for example, from this particular point to this particular point. It is moving from cold region to warm region. And so you take the difference between the point, forward point to backward point, and multiply with -1. So if it is warmer here, if it is less colder here, this minus this will have a positive value, but it is going to bring in cold area advection. So mathematically, we have this particular kind of movement of the parcel would reduce the temperature. So the same thing is being explained. So in this particular case, if it is going to be positive, that means if the decrease is, if the change of the temperature is higher as it moves in a positive direction, that contributes negatively, dou T by dou S. So the same thing we are explaining conceptually how it is called cold air advection, and vice versa can be understood very easily. So expanding the components, the advection we are writing minus v dot del t, you write minus u dou T by dou x. That means the velocity is now split into two horizontal components of the wind, u dou T by dou x minus v dou T by dou y. So minus v dou T by dou y is this particular part, minus u dou T by dou x is this particular part. So combining these two will give the change. That means the advection that is taking place between the 2 points. Mathematically, we are showing that. So the coming back, the momentum equation, that is the equations of motion, also called conservation of momentum. So the momentum equation, d by dt of u is equal to, now I'm writing these things are not known to us. This Lagrangian derivative or material derivative is equal to, now that's a parcel which has actually changed its properties because of its movement. But how the parcel changes is actually controlled by the dynamical part. I think at least in the second lecture, I don't remember the name, but he has explained the various forces. This is called the pressure gradient force. This is the gravitational force. This is the Coriolis force. This is the frictional force. And the pressure gradient force and the gravitational force are real forces, whereas frictional force also, whereas the Coriolis force is an apparent force which comes into picture because these laws of motion, the equations we know have to be applied to a coordinate system that is rotating. That's called non-inertial. Inertial coordinate system, Newton's laws of motion are valid, but we have a coordinate system which moves with the Earth, so it is called non-inertial, and you have to make corrections. I don't go into that particular one, is a very big part. So you have a series of forces that act on the parcel which makes it move. So previously we had talked about something, the change of the parcel individually, there's some particular kind of physics, etc. But here is a way the movement takes place, which is being controlled by pressure gradient force, gravitational force, Coriolis force, and the frictional force. So this is the Lagrangian form, du by dt, and the concerning Eulerian frame, dou u by dou t is equal to minus u dot del u. So the advection, because du by dt is equal to dou u by dou t plus u dot del u. So we don't do dou u by dou t will be equal to, you bring that advection term onto this side. So dou u by dou t is a partial derivative or the Eulerian derivative. And the first term on the right-hand side of this equation will be an advection term. In this particular case, these two terms are already included, or the advection term is being included into this. So rest are pressure gradient force, gravitational force, Coriolis force, frictional force. These, I presume that you know about the characteristics of these forces, very important. Somebody would deal with otherwise. So I will see a review, Eulerian, the conservation of momentum or the equations of motion. Full scalar form I have written. Somebody might have derived them for you already previously, but otherwise these equations are the defined equations which we be using in a scalar form, not vector form. So I have written these things are being expanded into the various U component, V component, W component, U, etc., all of them. So these equations are very, very important. They are the fundamental equations that denote the conservation of momentum or the equations of motion. So we know we talked about all this only for the equation of motion. That's what I was given as a topic for my lecture, Lagrangian, Eulerian, how to connect them. I did that, and I have shown the vector form here. So the scalar form I have given to facilitate your understanding much better. And coming to some other equations, though not given to me, I just mentioned these things. Somebody will teach you that. So the equation of continuity or the conservation of mass in the Eulerian form, you will have this, the density. So dou rho by dou t Eulerian is equal to minus del dot rho v. And this the one, the Lagrangian form of the equation is 1 by rho d rho by dt is equal to minus del dot v. Otherwise, the Eulerian form is here. The same thing is being expanded in two terms. And in the scalar form, it is being written. So I presume that the equation of continuity, its characteristics, how to get it, are already given to you. And this is another fundamental equation, that the thermodynamic energy equation, which comes from the second law of thermodynamics. Cp is the specific heat at constant pressure, temperature, alpha is the volume, Q is a diabatic heating term. And we also use the potential temperature. I am not defining, but this is very well known. I taught what is this in the atmospheric thermodynamics in the first lecture series. So I presume that why we are using this theta is a definition, because this is a conservative property. We can write using the potential temperature. The thermodynamic energy equation is written d theta by dt is equal to Q, or if it is purely adiabatic, then this will be 0. Or again, in the Eulerian form, it is dou theta by dou t is equal to minus v dot del theta plus Q. So I have given the forms of the thermodynamic energy equation, Lagrangian, Eulerian, conservation of moisture. Q is the specific humidity, d by dt of that is S is some kind of sources which gives the water vapor addition or takes out of it, source or sinks in mass per unit volume. Rho is the density, Q is the specific humidity. So the Lagrangian form is d by dt of Q is equal to S by rho, or the Eulerian form is dou by dou t of Q is equal to minus v dot del Q plus S by rho. So this is the conservation of moisture. And another equation we know, P alpha is RT, and this doesn't use any derivative. It's a diagnostic equation which relates the pressure, density, and the temperature. Well, these are the equations which are very, very important, fundamental equations. Conservation of momentum, that the equations of motion, conservation of mass, equation of continuity, conservation of energy, the thermodynamic energy, conservation of moisture, equation of continuity for water vapor, and ideal gas law. These are the fundamental equations which are being used time and again. Here in this lecture, I have given you just an information about the connection between the Lagrangian form, Eulerian form, and I have explained why both of them are being used in meteorology, in understanding the change of the atmospheric behavior, how the atmospheres get into motion, how the physics come into picture, how to represent them mathematically. I have tried to show that. And coming to its application, mathematically, these are the set of these equations. Here, these are the equations. Some have only all, otherwise, all of them have some particular kind of dou by dou t, dou by dou t, dou by dou t of u, dou by dou t of v, dou by dou t of w, dou by dou t of rho, then dou by dou t of theta, dou by dou t of q. All of them are the derivative partial differential equations for momentum, moisture, temperature, density. All of them are being, so these equations are being used in meteorology, mathematical writing as partial differential equations. And these are also non-linear because most of the terms which we have seen here, this product is a non-linear term because they both vary individually. So that's all equations more or less are non-linear. And so we have to use some particular kind of numerical methods. So all these equations set to or combined, blended together, formulated, make approximation to simplify them or use them as they are, and then try to make some mathematical numerical kind of solutions like a finite difference methods to use all of them, or a spherical harmonics method to use them. And these are the prime equations which are used time and again. They are the partial differential equations. They are integrated forward in time to estimate the future state of the atmosphere. And so these are the basic equations in meteorology that are being used. I have just tried to give a relation between the Lagrangian Eulerian form, how they are both mixed in this in the derivation of these equations. So there is a lot to go forward. I think the speakers that follow will make use of this, will build upon this. So I think there I end. I think I have exceeded, maybe not much, but still we have some time. Good for questions. I would be very happy to see any questions or comments from any of the participants. Thank you.
Thank you very much, sir. Before we go to the question answer session, can we take a photo quickly?
Okay.
I want you to unshare the screen, sir, so that we can put in gallery mode. I request everyone to please switch on their cameras. Karmakar sir and Swagata, Dr. Swagata. Ashwin, can you take?
Waiting for Swagata, sir.
Yeah, you can take. Maybe Swagata
Okay, yeah.
may not come.
Not visible. Swagata.
Okay. Yeah, so I also request Ashwin to please moderate the question answer session.
Thank you for your lecture, Bhaskar sir. There are 3 questions in question answer section. First question is, are these 2 kinds of forms 2 different perspectives?
Yes. In one way, both are very widely different in the sense I have explained in the beginning itself. Lagrangian is the way in which we follow a parcel, an individual parcel, try to understand the changes of the parcel's properties as it moves from one particular point in time. Whereas in the Eulerian form, we just fix it to certain locations and we try to see how the properties of the atmosphere change at those particular locations. So there is no concept of parcels in the Eulerian form. That they are widely different.
Okay, so next question is, how does advection contribute to the transport of heat and pollutants in the atmosphere?
The advection is V dot del of something. For example, in the case of temperature, vector wind dot del operator on the T, that means U dou by dou X plus V dou by dou Y plus W dou by dou Z. In the 3 dimensions, the wind components will advect a property, in this particular case, temperature, from one particular location to different locations as per the wind field. I have tried to explain the advection term. If a parcel is moving from a colder place to a warmer place, it will advect lesser temperature to the new location where it would arrive. And so it would be advecting colder temperature. The temperature where this mass will go is going to decrease. So advection means it's a property that is being advected by the wind. So because of that, the characteristics of the atmosphere would change.
Our next question is related to Eulerian approach. So based on this, how can one identify a suitable place for observatory setup, and how can you demonstrate this?
Setting up of observatories, normally what we wish is we would like to have observations coming from at a reasonably good density in the volume of the atmosphere that we consider. Why? Because the properties of the atmosphere change very, very too quickly, and we want the observations to be available at as less distance as possible. But taking the observations in the Eulerian form is very difficult, in the sense that you have to spend a lot of money to establish each observatory where observations could be taken. In the last 2 decades, several advancements have come in. Previously, for example, in India Meteorological Department used to have fixed observation localities where observations used to be taken. But now the automatic weather stations and many other particular kind of things, so surface observations became very, very easy and more dense in this. So though we wish, there are many constraints of having these observations in the dense way as a meteorologist likes to. And this is the reason why the Indian government has started a Mausa mission. The Prime Minister of India has started a Mausa mission. He announced the Mausa mission just at the beginning of this year, allocating at least more than 1,000 crores for this. I don't remember how much money has been allocated, mainly to increase the density of the observations. That's very, very important. Unless we have the observations in the Eulerian form, we can't make a good analysis, and then that would help the models to perform well. So.
Next question is how pressure gradient force behavior will vary on an air parcel during instability conditions and normal weather conditions?
See, these two are slightly different. Why? Because pressure gradient force, the parcel or the parcels of air would move from a region of high pressure to low pressure. That's a natural way. Where the density is very, very high, where the pressure is very, very high, the air would move from the region of high pressure to low pressure. That's a dynamical force which acts on it. Stability, instability, I don't know what the person who put the question indicates a thermodynamic way. How the atmosphere is, so a parcel which is rising in the upward, whether the parcel is going to be stable or unstable, it is going to depend more on the temperature structure of the atmosphere and how the parcel is moving up and down, which we have talked about in the atmospheric thermodynamics in the first lecture series very elaborately. So one is a physical force, another is a dynamical force, which we are trying to, both of them apply on the air parcel at the same time, but both have different properties and the conceptual one. So both acts differently, but a pressure gradient force is on a much larger scale than a partial scale, which is applicable for the atmospheric stability. Pollution is very much different. So actually pollutant dispersion is being made. You should have some particular, whatever that is, the stability of the atmosphere plays a very, very important role at the lower atmosphere where the pollutants are being released, how the dispersion would take place. All that happens in the atmosphere is very, very stable. Then the dispersion would be very, very slow and the contamination by the pollutants will be very, very high. So in that particular case, normally what we do is we get the information of the wind field, the temperature field, or the stability thermodynamics we use, and then get the physical state of the atmosphere. And we'll try to use that to see the pollutant dispersion using another model. What we call dispersion models are now available. We try to use them to get the dispersion under various atmospheric conditions. So pollutant dispersion, it's not by pressure gradient, but it is mostly happens in the boundary layer, atmospheric boundary layer, very near the atmosphere where the pollutants are being released. So it happens in the first layer, just above the Earth's surface, we call boundary layer, where the temperature structure is going to be different.
So next question is there any application where both frames are used in hybrid form?
They are already being used. I have shown you the material derivative, the local derivative, advection term, how these, because the Lagrangian derivative is a mixture of the local derivative plus advection. So we are using both of them. See, in these equations of motion, we are using both of them together, though not spelt one. But the remaining things actually makes it look like more Eulerian, because we only talk about dou by dou t, dou by dou t, dou by dou t, which is the local derivative, because in the Eulerian form, the analysis and the application of numerical methods, mathematical methods is much more easier. So otherwise, they both are now linked together. So as I said in the beginning, the material derivative, where do the physics go in? Here we have not talked about that. It's going to be a very, very long way. How the physics is being introduced, how a parcel is going to be heated, whether it's going to be less denser, how it rises or sinks, whatever that is happening, that's a Lagrangian way. So both are being there. In the beginning itself, in one slide I have shown, we will be using the Lagrangian framework for including the physics. We use the Eulerian form for the dynamical framework. Both are being now used together. They are not de-linked.
Next question is, are Lagrangian and Eulerian are the numerical methods to find the particular variables at a point with coordinates with time?
Yeah, Eulerian we use very frequently. We have the coordinate system, and using that we observe the rate of change of the atmosphere at different locations. Hello. So both are, I'm sorry for the disturbance, but we use the Eulerian form for the normal. The one Lagrangian is being used in some quasi-Lagrangian we call. There are some particular models which are specifically developed for this.
So now last question, as I can see here, is environmental lapse rate associated with Eulerian framework or Lagrangian?
Lagrangian. We use that.
Okay, so no more questions I can see here. So yeah, thank you so much, sir.
There is one comment or question, I don't know, but it says, because of this Lagrangian and Eulerian frame of reference, during thunderstorm activity, we observe or find source and sink at different area or location. And because of this, sometimes models fail to capture this phenomena. A kind of statement, probably.
Oh, it's, you see, we are at the starting point. We are at the starting point. In order for us, we have not talked about any physics at all. How to include the physics in the prediction scheme, we have not talked about that. How a thunderstorm forms, how a cloud forms in the one, what kind of mechanism we have to include it into the numerical models. You see, there are many things. You can't include, you can't calculate the formation of the cloud in the way I have shown you. But we have some parameterization schemes which come into the picture. Though I have shown you dou theta by dou t is d theta by dt is equal to some q. Where is the diabatic heating coming in? If you talk about only the advection, what about the diabatic heating? So all that has not been dealt with. As probably you learn further, we will see. Maybe not even in the atmospheric dynamics, but when you go to next course on numerical weather prediction, then we will see these problems like physical parameterizations, how to parameterize the radiation, how to parameterize the convective process, how to parameterize the micro cloud process. All these things are Lagrangian mostly. You see, they cannot be included directly, but they have to be included in order for us to have weather prediction. So that comes at a later stage, but I think it is too early for us to talk at this particular time. Thunderstorms, we are predicting using numerical models, but we are having some physics into it, how to embed physics into that, to deal with how the cloud can take place. All that is a different particular one, which has to be linked with the dynamical framework. So my lecture today is only the basics of the dynamical framework, in which how to distinguish, how to see the difference between the Lagrangian and Eulerian forms, how we connect them in the equations.
Thank you, sir. So before we go to the vote of thanks, I would like to give some statistics. So almost 204 participants attended this lecture, out of which 170 have rated it as excellent and very good. So we are very happy. Of course, sir gives it, and it's always a pleasure to listen to sir. So really very nice.
Yeah, I'm very happy that the students feel it better, because basically I'm a teacher, and
yes.
I like to start at some point where we try to give all the information. So I don't know, sometimes maybe people think that I'm too fussy, but so I made some statements in the beginning, which I thought are very much important for the student, on what basis, how we build up the two particular types of framework. So if that's going to be, because basically all of us know all these things, but these are meant for the students who are trying to listen after the thermodynamics. So they should be able to understand what are the basics of this, so that they can understand the next lectures much better. Thank you very much.
Thank you, sir. So now I request Dr. Mili Ghosh Nilala to please give vote of thanks. I'll share the screen, ma'am.
Yeah, thank you. Thank you, ma'am. On behalf of the organizing committee, I would like to thank each one of you for your contribution for this fourth lecture of weekly online lecture series on atmospheric dynamics and its application to climate sciences. Firstly, I would like to thank Dr. Samarendra Karmakar sir, former Director Bangladesh Meteorological Department and advisory panel member of SAMA, for giving welcome address and brief information about the lecture series. My deepest appreciation goes to our speaker of the day, Professor Dr. D.V. Bhaskar Rao sir, Honorary Professor retired, Andhra University, for delivering wonderful and very informative lecture on component-wise equation of motion in rectangular Cartesian coordinates, Eulerian and Lagrangian derivatives. I also thank Dr. T.V. Lakshmi Kumar for introducing our today's speaker, Professor Dr. D.V. Bhaskar Rao sir. My heartfelt thanks goes to Dr. Rohini ma'am, the program convener, for moderation of today's session, and Dr. Ashwin for nice conduction of question answer session. I want to thank all the panelists for their guidance and constant support for each and every minor detail. I extend my thanks to all the participants and attendees who joined us from across the globe. Finally, sincere thanks goes to the students and scholars of Savitribai Phule University who are involved in organization of this lecture, as your contribution matters a lot. Thanks a lot.
Thank you very much, ma'am. So next, just for the participants, the next lecture will be on 15th of February, which is Saturday, and it will be delivered by Professor P.N. Sen, who is retired from IMD and working as a visiting professor in SPPU. So thank you, sir. Sir, Someshwar Das, sir, any comments?
Thank you so much for conducting the session so nicely. And thank you to Professor Bhaskar, sir. He is
Yes, sir.
teacher of most of us.
Yes, actually, we are learning from you.
Yeah. So thank you so much, sir, for delivering the
Thank
nice.
you, everybody. Thank you. And thanks to Dr. Rao for
Thank
his
you.
nice lecture. And really, it is very encouraging for the beginners in the field of dynamic meteorology. Thank you, Professor.